It's like Calc 2. Wow.
What is wrong with you?
That was kind of savage. I like it. Honesty or decorum. Shane chooses honesty. Very good. See, I circled back to it, Mary. Are you happy? That's good, right?
Wow.
So you and Jack made plans yet, or?
I'm a little confused. Why did Mr. Young email you? My hand hurts.
Yeah. Well, anyway, okay, I'll begin with a word of prayer. We do need to do complex today, and even if I do skip many proofs, we still have to get stuff covered. So, Dear Heavenly Father, we thank you for this day. Again, I thank you for this class and these students. Just ask you to bless our work today. Help us to just understand a little bit about Laurent series and how to work with them and what they mean, Lord. In your name I pray, Lord Jesus. Amen. So I'm actually going to start with what we mean by function being analytic at infinity. So that was something we missed, and here's the definition. So we're going to talk about power series expansions at infinity, basically. Definition. Function f of z is analytic at infinity if g of w equal to f of 1 over w is analytic at w equals to 0. All right. Okay. So let's look at some examples of this. Example 1, kind of a silly example. F of z equals to 1 over, say, z minus z naught. All right. So this function, we want to decide whether or not, obviously this is analytic where? This is going to be analytic everywhere except for z equals to z naught, right? So this thing's analytic on the plane punctured by z naught for sure, but is it analytic at infinity? All right, let's judge it. So if we look at g of w, which in this case would be equal to f of 1 over w, which is what? 1 over w minus z naught. All right, I want to find the power series expansion of that at 0. I mean, actually, all right, so let's see here. If I rewrite this, multiply by w top and bottom, what I have, I've got w over 1 minus z naught w, right? Multiplying by w over w, right? Agree? And now we can use the geometric series and rewrite this as what? This is the sum n equals 0 to infinity of w times z naught w to the n, which of course is the sum n equals 0 to infinity of z naught to the power n w to the n plus 1. So my question then is this analytic at w equal to 0? You know, so you should understand that this definition is made with the understanding that we're not just going, oh, this doesn't make sense at 0, we're done. Like, this is subject to the kind of simplifications I'm just making, all right? And the answer is yes, it's analytic at w equal to 0 because I just did what? I showed you that you can represent f of 1 over w by a power series centered at 0. So yes, g of w analytic at w equals to 0, which implies that, you know, f of z 1 over z minus z naught is analytic at infinity. All right, let's do another one. Example 2. I'll make my life a little bit easier. What if I had like f of z is equal to like 1 over z to the power 10 plus 1 over z cubed, right? Is this analytic at infinity? Well, if we look at g of w equals to f of 1 over w, and we simplify, so we got 1 over w to the 10th power, right, plus 1 over w to the 3rd power. Well, we get w to the 10th plus w to the 3rd power. Is this analytic at 0? Yes, yes, this is analytic at 0. So therefore, you know, f of z is analytic at infinity. All right? So, great. Let's look at another example. How about f of z equal to, say, sine of z? This one, right? This is, you know, this is analytic everywhere. This is an entire function, right? It's holomorphic on the whole complex plane. But is it analytic at infinity? Well, let's find out. Now remember that essentially a definition for this function can be given by the power series, n equals 0 to infinity minus 1 to the n over 2n plus 1 factorial times z, oops, my bad, z to the 2n plus 1, right? This could be taken as the definition of sine, right? So g of w is f of 1 over w, right, by construction. That's what we're trying out. And that would be the sum, n equals 0 to infinity, minus 1 to the n over 2n plus 1 factorial times 1 over w to the 2n plus 1 power. All right? Let me write it out. Let me write this out here. So like what we got explicitly is something of the form 1 over w minus 1 over 6w cubed plus 1 over 120 w to the 5th power plus dot 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 dot. So what can we say? G of w, is it analytic at you know, at 0? The answer is no. No, it is not. And I guess that partly rests on some theory that we're going to talk about today. But it turns out that in a certain context, which is almost always, we can write down what's called a Laurent series for a complex function. And the Laurent series will have a very specific form if the function is analytic at the center of the Laurent series, and otherwise it's not analytic. It's got a singularity at the center. Those singularities we're going to learn, there are 3 kinds. There's either removable, a finite singularity, or an essential singularity. All right. This is an example of an essential singularity. It's an essential singularity because there are infinitely many reciprocal terms in the power series expansion. Well, the Laurent, this is technically a Laurent series. So Yeah.
So functions that we think would be analytic typically at 0 aren't necessarily analytic at 0. Like for sine, like if I'm just looking at that,
Oh yeah.
I think it would be analytic at 0. But it's,
Yes. Yeah. So like sine, yeah, sine is analytic at 0. So analytic just means it has a power series expansion, which represents the function near the point. And we learned that if the function's holomorphic, it's analytic, right? So, yeah. Functions which are not analytic, mostly I think we have examples of, I mean, what are examples of functions which are not analytic at a point? Like, let's see here. So, some common examples of functions not analytic at z naught. How about this? I'd start out with 1 over z minus z naught, like that's the quintessential one, right? That's not analytic at z naught. You could do 1 over z minus z naught to the m for m greater than or equal to 1, actually. Yeah. Square root of z minus z naught. Principal square root is not analytic at z naught because it's defined in terms of, I mean, really it's the man behind the curtain here is just this guy. Yeah. That's not analytic at z naught. It's not even analytic in like a punctured disk around z naught, right? Because you necessarily have that branch, that jump branch cut. In contrast, these are analytic on a punctured disk around z naught, right? You can do that. That's all. I mean, basically, there's like a kabillion examples that you come up with are just, various ways to mess with log, right? Like z to a complex power. Well, maybe z minus z naught to a complex power, right? If that complex power requires, the use of the log, right? If this doesn't, like, there are examples where that use of the log is like not necessary, right? Like for example, c equals 2. I don't need to write this way, right? C equals 2 is the square. Integer powers, certainly we don't really need to formulate in this way. But complex powers, yeah. Okay, anyways, that's that. Let me move on here. So there's some examples. How about a polynomial of order n? Would a polynomial of order n be the analytic at infinity? What do you guys think? Pn of z equals, like z to the n plus a2z squared plus a1z plus a naught. This would decidedly not be analytic at infinity because, in this case, g of w would be Pn of 1 over z, which would be equal to like 1 over z to the n plus a2 1 over z squared, a1 times 1 over z plus a0, right? So this is, my bad, I was supposed to do 1 over w. Sorry, I'm trying to stick with the notation I was using. So this is certainly not analytic. I can't spell. And w equal to 0, so therefore f, well, not f, but in this case, Pn of z not analytic at infinity. All right. Okay, so now that we have that definition hopefully settled and some examples, let us go on. Um, so here's another definition involving infinity that we should take a stab at here. Definition. This is my definition 8.78. All right. So let F be analytic on some exterior domain modulus of z greater than r for some positive r. All right. If f is not identically 0 for z larger than r, then we say f has a 0 of order n at infinity if what? Can you guys complete the definition for me? I'll get you started. G of w equals to f of 1 over w has a blank of order blank at blank. I got 0. I'll take that. Very good. Order n at w equal to 0. So close, but actually very far away. Sorry. I was inspired by Shane. Let's see here. I accept it. So, and we have characterizations of what it meant to be a 0 of order n, right? So like, let's see here. So, if we can look back at my examples thus far, if we go back to like example 2, what would this say right here? So no, if we go back to example 2, you guys tell me, what's the order? Does that have 0 as a 0 for w? Like g of w is 1 over w. We got w to the 10th plus w to the 3rd. Is w equal to 0 a 0 for this function? And if so, what's its order? How do we define 0, order of 0? Do you guys remember? So I'll factor out w cubed, right? We've got 1 plus w to the 7th. Yeah? So this right here, I can call, say, h of w. And it's, h of 0 is what? It's 1, which is not equal to 0. So this tells me that, g of w has 0 of order 3 at w equals to 0. Does that make sense? Now, so let's work on a theorem here. This is my theorem. .79, and I kind of feel like I should Well, I don't remember the number for the other theorem I'm thinking of, but let me just state a theorem. If f of z is holomorphic at z naught and has 0 of order n, then there exists h of z holomorphic at z naught with h of z naught not equal to 0, and f of z is equal to z minus z naught to the power n times h of z. All right, this is the analog of the theorem 8.79, which I'll do next. But I think this is probably good for us to do this because I talked about it, but I don't think you guys know this stuff yet. But it does matter. And we should all be able to prove this. So, all right. I guess the question is, how do we define a 0 of order n? And so we have to pretty much, so we proved earlier that there was an equivalence between being able to factor out this and also being able to say that all the way up to the n minus 1th derivatives were 0, and the nth derivative was non-zero. Right? For a polynomial, we can either define 0 directly in terms of polynomial algebra, or we can define 0 in terms of vanishing of derivatives. You see, we have to use vanishing of derivatives to define the order of a 0 for a general function because it's not a polynomial, so we can't very well, factor something out of something that's not a polynomial. So just to be clear, our definition for the order of a 0, f of z, holomorphic at z naught, has 0 at z naught of order n if f of z naught is equal to 0 and f prime of z naught is equal to 0, and so forth and so on. N minus 1th derivative at z naught equals to 0. However, f to the nth derivative at z naught is not equal to 0. This is how we define a 0 of order n. We need to use calculus. All right? My claim then is that if you make that calculus-based definition of a 0 of order n, well, good news. The corresponding sort of factor theorem-based definition actually still works with the understanding that you're using the power series for the function, yeah? So like, is this clear? Do I need to talk more about this? Are you guys on board with what I'm saying here?
Yep.
Okay, so let's go then. So what's the deal? The proof is very simple. F of z is equal to the sum n equals 0 to infinity of the, let me not say n, let me say j. Sum j equals 0 to infinity of the jth derivative evaluated at z naught divided by j factorial times z minus z naught to the power j, right? Since f of z is holomorphic, it's analytic, as we proved before, right? But what are we given? We're given that it's a 0 of order n. So what happens to that summation? All the way up to order n minus 1, those are all given to be 0. The coefficients are all 0. So this is equal to the sum j equals n to infinity of the, jth derivative at z naught over j factorial times z minus z naught to the power j, as f j of z naught is equal to 0 for all j ranging from 1 to n minus 1. And then we just need to factor something out here. So this is the sum, j equals n to infinity, the jth derivative at z naught over j factorial times z minus z naught to the power n, z minus z naught to the j minus n. That's a legit calculation here, because why? Because j starts where? At n, right? So like I'm not doing any kind of funny business here. I mean, I guess you could still do that if your sum didn't start there, but then you wouldn't be doing polynomials anymore. You'd have what? You'd have like division. If j minus n is negative, then you'd be, like factoring out a reciprocal power. You could do that, but it wouldn't get us where we want to go. So this doesn't depend on j. I can pull it out. And notice here that this piece right here we can call h of z, right? It's clearly analytic because we already know that the series converges. I mean, this is essentially a tail of the convergent series for the Taylor series that we're already given at the start of this, And what happens when we look at h of z naught? So this is 0, right? So if j minus n is greater than or equal to 1, this is just 0 to a power, so it's 0. The only thing that can non-trivially contribute to this series is the j equals to n case, which is the start. And what does this become? It becomes the nth derivative at z naught divided by n factorial. And is that non-zero? Yes, it is. By assumption that we have a 0 of order n, this is not equal to 0. Consequently, the theorem. So there is essentially a factor theorem for power series, right? I sometimes call this the factor theorem. So the theorem 8.79 that I was getting to in the notes is a corresponding result for infinity. If f of z is analytic at infinity with a 0 of order n, then f of z is equal to oh man. So I've got a z naught in the theorem. I don't understand why I have that there. Well, I mean, I guess I could. Sorry, it's weirding me out. A sub n over z minus z naught to the power n plus a sub n plus 1 over z minus z naught to the order n plus 1 plus dot 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 plus dot dot dot, yeah. Now my examples have the z naught essentially equal to 0 there. All right, well. So what would the proof to this look like? If f of z is analytic at infinity with a 0 of order n, that means that we have g of w, right, equals to what? W, well, w to the what? W to the power n, right, times h of w, where h of 0 is not equal to 0, right? That's what it means for f of z to be analytic at infinity with a 0 of order n, where how is this g I've introduced related to the f? G of w equals to what?
F over 1 over w.
1 over w, right? If this is true, right, translate that into an equation that allows us to go from g back to f. What would that be? What would f of z be equal to in terms of g then? F of z equals to what in terms of g?
G of 1 over z.
G of 1 over z. That's right.
Then you can use partial fractions.
No, then we can just substitute. So, and maybe the theorem's wrong. Let's see here. So, f of z is equal to 1 over z to the n, right, times h of well, h of 1 over z, I suppose, right, which is going to have the form a sub n over z to the n plus a sub, n, I don't know, what a sub n plus 1 over z to the n plus 1 and so forth. Where I'm using the, I'm supposing that h of z has coefficients. I'm supposing here that h of z is like an plus an plus 1 times w plus an plus 2 times w squared and so forth. So I'm using these as the coefficients for the power series expansion for h here, which I don't have room to write down. But it doesn't, yeah, I don't, yeah. Although I think you can get from here to there if you want. I mean, you could take this and rewrite it as such. I don't really want to do that. I don't think this not really what I'm after today. So I don't think the claim of the theorem is wrong. I just don't think it's like super easy to get to directly from this theorem. Because I'm pretty sure that my notes are claiming that this is essentially a corollary to that theorem. And I do think that's true if you make the result of the theorem just not z minus z naught, but just 1 over z to the n. That is pretty clear. To get from here to here, I would do my I can think of different things. The one thing you could do, kind of like you said partial fractions. I don't know if I'd quite say that, but I could, trade z for z minus z naught plus z naught to the power n, expand that, and no, I just don't want to do it. I'm just going to put a question mark right here at the moment. I have doubts about theorem 8.79. All right. But I'd like to show you some other calculations which I don't have doubts about, and I'd also like you to be able to do. So let's do that instead. So up to this point, like the main thing I hope we learned today is like if we want to talk about infinity, we can trade the question for a corresponding question about 0 for the function that's defined by just taking your function that's given and, evaluating it at the reciprocal function. So there's like this cool connection between 0 and infinity in this way, which is nice. Because 0 is pretty easy to understand, whereas infinity, All right, so here's another calculation which I think is worth looking at. What example am I on? Example 4?
Example 5.
Example 5. Oh, wow. All right, so here we have f of z equals 1 over 1 plus z cubed. All right. And then the question is this, analytic at infinity? So we'll consider, actually, rather than doing the thing I've done up till now, I want to introduce a new viewpoint, which is that we can go backwards from the theorem I just said. See, if f of z has, 0 of order n at infinity, then f of z equals to what? A sub n over z to the n plus a sub n plus 1 over z to the n plus 1. Is that right? Isn't that what we just worked out?
Yes.
All right. My point to you is that if you can find the expansion of the function in the reciprocal powers of z, you can read from that if this is in fact analytic at infinity and if it has a 0 of a particular order. All right? So the question is, can we expand? Let me just put a question up here. Can we rewrite this as a 1 over z expansion? All right. So what I've done in the notes is different. All right. But I'm ignoring, the notes, they just go through the g of w equals to f of 1 over w idea. All right. But let's go a different way here. So how about this? If I divide the top and the bottom by z cubed, what do I get? Right? Divide the numerator by z cubed, 1 over z cubed. Divide the denominator by z cubed, 1 over z cubed plus 1. Hey, geometric, yay! So this is the sum, n equals 0 to infinity, of 1 over z cubed times minus 1 over z cubed to the power n. So I'm going, geometric series, a equals to 1 over z cubed, and the ratio is minus 1 over z cubed, right? Because we're always trying to match the a over 1 minus r pattern, right? So, hey, checked out. So we've got sum n equals 0 to infinity of like minus 1 to the n, 1 over z to the what? 3n plus 3, I think. All right. And so if I write those out, what do I got? Like n equals 0 gives me what? 1 over z cubed. And then what's next? 1 over z sixth plus 1 over z to the 9th, and so forth, right? So what this tells you, among other things, is if you were to look at the g of w equals to f of 1 over w, what would you get? You see, just plug 1 over w into here, what do you get? You get, yeah, w cubed minus w to the 6th plus w to the 9th and so forth, right? Which, of course, we could easily factor a w cubed out of to see, well, that has a 0 of order 3 at w equal to 0, corresponding to this showing me, we have 0 order 3 at infinity. But I can see it directly from this right here. So this is a Laurent series. Again, where is this Laurent series defined? This step right here, where is this legitimate for? What's the condition going from here to here? What's the terms and conditions that are applied? We need that the ratio of the geometric series is less than 1. But the ratio is minus 1 over z cubed. So this gives us 1 over the modulus of z cubed is less than 1, which we could, of course, rewrite as 1 is less than, right? Or perhaps more civilized. I just that's the way I like to look at it, yeah? So this is legitimate out here, where we have modulus of z greater than 1. That's the domain on which this calculation is legitimate. This is the Laurent series representation of f of z on that outer annulus, centered at 0. You could center it somewhere else, right? If you wanted to. I don't think I want to. This one would be unpleasant. All right. Excuse me. I'm going to skip some of the details, but I'm just going to kind of give you a snapshot of the before and this one's kind of a cool example. Example 6. Here we have f of z 1 over z minus z naught to the power n. All right. What do you think about this one? What's the order? Does it have a 0 at infinity? If so, what's its order? What do you think? Probably so, right? I mean, intuitively speaking, shouldn't it be obvious that it has a 0 of order n? What's the difference between 1 over z and 1 over z minus z naught, as if you think about the vantage point of infinity? It should, yeah, I mean, it should be the same thing, right? So the calculation of that is given here. See, like 1 over z to the n, I guess I'll write it out. Z to the n minus z minus n z to the n minus 1 z naught plus stuff with binomial theorem n z minus z naught to the n minus 1 plus z naught to the power n, so just expanding. All right, and then just factor out, I've offended Violet. Let's see here. 1 over, factor out a z to the n, and you'd have 1 minus what? N z to the n minus 1 z naught plus plus n z z naught to the n minus 1 plus z naught, all divided by z to the n. Which, if you do an algebra step, you can see is actually 1 over z to the n times 1 plus n z naught over z plus dot 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 minus n z naught to the n minus 1 over z to the n minus 1 plus z naught to the n over z to the n plus dot dot dot. I think that should be a plus. Well,
I think it would,
was that supposed to be a minus?
that one's supposed to be a minus, yes.
Ah, if that one's supposed to be a minus, then this.
All the ones with coefficients n.
Yeah. Well, anyway, let me not belabor this too much here. But the point is, like, do you understand how to go from here to here? Like, what's going on there?
It looks like shady factoring.
Looks like shady factoring. Yeah. It's worse than that. So what's going on there is using the geometric series, thinking of all of this as like r.
As what?
R.
Oh.
This is 1 over 1 minus r. You know, the giant reciprocal's gone, right? So it's, I mean, this is something you can do. 1 over 1 minus r is 1 plus r squared plus dot dot dot, right? The thing is, for this r, you've got what? You've got things that are what? Like reciprocal in z up to 1 over z to the n. So when you take powers of that, you still have things that are reciprocal in z. Like there's no way you can get a polynomial in z from that. Which means that as you power up, you've still just got reciprocal terms. So like everything past this, it's still just reciprocals. And that one there is really what we need, because this, if I, you know, because if you go back to the g, like g of 1 over w, right? You get w to the n, and this just becomes like 1 plus powers of w. So this h of w, when you plug in 0, you just get 1. So actually this shows that it has a 0 of order n at infinity. Although I do wonder if it's actually pretty easy just to go back to the other, like the basic definition and show it directly, you know? Like g of w. Let me just, f of 1 over w, right? So you have what, 1 over w minus z naught to the power n, which you could rewrite as w to the n over 1 minus z naught times w to the n, right? Which you could just rewrite as w to the n times 1 over 1 minus z naught w to the n power, right? And it's actually very clear that that is analytic at w equal to 0. And what's its value? If I call this thing h of w?
H of 0 is 1
h of 0 is clearly 1, right? So this proves that this function has a 0 of order n at infinity. So you're like, well, why is this calculation in your notes? Well, I got it from Gamelin. I think it's a cool calculation. That's why I left it there, all right? But I mean, if you're just after the conclusion, namely that this has a 0 of order n at infinity, well, then this argument down here is like way easier, right? So anyway, just saying. Let me move on here. So there is a, what's the word? A leisurely way to introduce Laurent series, and there is a fast way. We are going to go with the fast way. All right. So, in short, I'm going to give you two things. The first is just a definition of a Laurent series in the abstract. All right, kind of like you define a power series before you think about it being a function, just as an expression. So, like, here's what I mean by a Laurent series as an expression. A Laurent series has a center, so centered at z naught has the form some m equals minus infinity to infinity of a sub m z minus z naught to the power m. So it's just a power series paired with a infinite sum of reciprocal powers. All right, so like, I guess I could attempt to write it sort of with plus dot dot notation, that is, so we could have like dot 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 plus a sub 2 over z minus z naught squared plus a sub 1 over z minus z naught plus a sub 0 plus a sub 1 times z minus z naught plus a sub 2 times z minus z naught squared plus dot 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 dot. So you decided to forgive me. It's good. It's good. I forgive you as well. See?
Heartwarming.
I know, right? In this, bitter partisan season, it's important for us to maintain channels of communication with people with views other than ourselves. So.
Mostly about math.
Yes, mostly about math. Very good. Yes, sir. So this, what I was just defining, Violet, is this is the Laurent series.
Anybody else left class?
Huh?
Can't do this with anybody else left.
I could do it. I could do it.
You told me out when I was leaving.
Yeah.
That's because you left right after you got here.
I
She was in the middle of class all the time.
I call out people leaving. I call out people leaving physics.
What are you
I do.
talking about? I won't go twice.
Hey, listen, my lights were going off in physics, and the other day, like the lights were going off, I accused a student of being the reason for it. So I am all about unjustified accusations. It's part of it's part of my pedagogy. Yes, and inventing fake relations is one of like the highest callings of my job.
I say you should do that for Violet now. Okay. She's unsatisfied with the accusations you form.
That is
You
true.
can't do that if you call me 12.
Well, that's mostly my son calling you 12, but
Well, you can't laugh at him calling you that.
but how could I not laugh at him calling you 12? Like, it's hilarious. Theorem.
Wow.
Theorem. So this is what a Laurent series looks like. It's an unending sum of positive and negative powers of the binomial, like, well, z minus z naught. All right, so suppose, here's the deal. Suppose 0 is less than or equal to rho, is less than sigma, is less than or equal to infinity. And suppose f of z is analytic for rho less than modulus of z minus z naught is less than sigma. All right? Then f of z has Laurent series representation. F of z is equal to a sum n equals minus infinity to infinity of a sub n z minus z naught to the power n, where the coefficients are given by a sub n 1 over 2 pi I integral around the circle centered at z naught of radius r, f of z over z minus z naught to the power n plus 1 dz. Right. Here r is greater than 0 with rho less than r less than sigma. And by the way, this is unique. I mean, there's a unique Laurent series in this sense. You can guess where that formula is coming from, right? The Cauchy's generalized integral formula, right? And if you look in my notes in the pages which precede this theorem, and this theorem is theorem 9.1.8 on page 135, you'll see that this is derived using exactly that theorem. So maybe it's helpful to draw a picture a little bit here. So the idea is z naught is here, and I'll picture it as if rho is, not equal to 0. So rho's out here somewhere. All right. And then sigma is out here somewhere, right? This circle that we're integrating around to derive the values of the coefficients of the Laurent series, where is it? Somewhere between those, right? So like the circle that the integral's taken over is somewhere in here, right?